Hello, my name is Jiaming Zha. I'm from High Performance Robotics Lab of UC Berkeley, advised by Professor Mark Mueller. Today, I would like to present to you our research about exploiting collisions for sampling-based multicopter motion planning. In the world of billiards, collision opens a lot of opportunities. For example, in this video, the player exploits collisions to find a path that avoids other balls on the table. Inspired by a similar idea, we wish to also exploit collisions when we are doing motion planning on collision-resilient autonomous aero vehicles. The video on the left is the tensegrity collision-resilient multicopter that we have designed. It can survive collisions with the speed up to 6.5 meters per second. We wish to create a motion planner that can take account of collision of this as well as many other multicopters with collision resilience. The result of our research is a sampling-based collision-inclusive motion planner. It can generate trajectories with collisions and can provide a better planning performance than similar sampling-based collision-exclusive planner in narrow spaces like tunnels. In the video on the right, our tensegrity vehicle is tracking one of the collision-inclusive trajectories generated by our planners. Here is a quick roadmap for our presentation. First, we'll briefly introduce two key tools our planner uses: the motion primitive generator and rapid collision detector. They enable our planner to quickly link sampled nodes with basic motion primitive pieces and detect if these pieces will collide with obstacles. Afterwards, we'll introduce the algorithm of the planner and analyze its cost and benefit. Last, we will show an experiment of tracking the collision-inclusive trajectory we have generated with our planner. So here we go. First, I would like to introduce the motion primitive generator tool. It can quickly compute a thrice differentiable trajectory which guides the multicopter from an initial state at time t0 to a final state at time tf, while minimizing a cost function as the integration of the norm of the jerk of the vehicle. This cost function is a heuristic for the aggressiveness of the primitive. Primitive with larger cost will be more aggressive and hence more likely to be input and feasible. The result primitive generator generates are in the form of fifth-order polynomials. The tool is extremely computationally efficient and can generate and check the input feasibility of about 1 million candidates in a second on a normal computer. The second tool I would like to introduce is a rapid collision detector. It can quickly detect whether a generated motion primitive will collide with a convex obstacle in the environment. The key steps of the detector are as follows. First, it generates a separation plane here that is tangent to the obstacle, with the norm of the plane pointing to the temporal middle of the primitive. Then it checks whether the primitive would cross the plane, as is shown here. If the primitive crosses the plane, it will then bisect the primitive with respect to time and check each pieces. If both pieces of the primitive does not cross the new plane generated here, then we know the primitive itself will be safe. For primitive lead to a collision, we can estimate the collision time by keep bisecting the primitive until the piece involving collision, like here, is smaller than the threshold. With the primitive generator and collision detector in mind, we now introduce our sampling-based trajectory planning method. The method is based on the RRT star algorithm with two key differences. First, we sample nodes in the free space as time-state pairs. The state of the vehicle is described by its position, velocity, and acceleration. Second, the sample nodes are connected with input feasible multicopter primitives with the lowest cost. Here, we use a quick example to go through the process to show how it works. Consider a planning step shown on the slide. The red circles are previously sampled nodes already added to the exploring tree, whereas the green hexagon is the newly sampled nodes. Now, we connect the newly sampled node with nodes in the exploring tree, which has a prior timestamp. The connection is carried out with the motion primitive generator. Here we assume T1, T2, and T3 is smaller than T, and hence we only consider these connections. Then we check the input feasibility of the connection. For example, we assume that primitive 1 here is input infeasible, and we will discard it. Then we will compare the cost of the feasible primitives and pick the one with the lowest cost. We will add the primitive and the sample node to the exploring tree and rewire the tree to maintain optimality. The trajectory between start node to any desired destination will be a concatenation of a series of motion primitives connecting the two nodes. Now that we have a mechanism to create the trajectory with sample nodes, I would like to also introduce how we are add collision, like the one here, into the consideration with the step of collision node generation. We use the following slides to show the process. First, consider this figure, which shows the beginning of the collision node generation process. The red circles again represent the nodes in the exploring tree. The green hexagon, which we'll show later, will be a newly sampled node. The blue rectangle is an obstacle, and we'll use the yellow square to represent the collision node. First, we sample the node and try to connect it with the exploring tree with a primitive of the lowest cost. Then, we check if the primitive collides with the obstacle. If yes, we compute the time and the state of the vehicle right before the collision, like here. Then, we'll replace the sample node with a collision node, which has the time as the collision time and the state as the state right before the collision. Moreover, we will use the collision model to predict the state of the vehicle after the collision. Notice that the collision model is vehicle-specific and may be different for different vehicles. Here, we present the model we use to predict the behavior of the tensegrity aero vehicle. We predict the velocity component normal to the obstacle with a linear function, where E is the coefficient of restitution. Moreover, we predict the ratio between the tangential impulse and the normal impulse to be proportional to the incidence angle, like theta on the graph. After generating the collision node, we can connect it to other sampled nodes. When the collision node is connected with other nodes with timestamp prior in time, it will use the state before the collision for the connection. Meanwhile, when it is connected to other nodes with a timestamp later in time, it will use the state after the collision, like S plus here, for connection. Planning with collision brings a huge benefit. Sample nodes will not be discarded due to collisions anymore, as is shown in this video. As a result, under the same number of steps, more nodes will be added to the exploring tree, and thus the tree will be likely to expand further, and hence the algorithm will be likely to find a viable trajectory faster. The planning with collision also comes with its cost. First, more computation time will be spent on the collision node generation step. Moreover, the collision inclusive planner may slow down the exploring tree expansion, as the collision node generator pushes the sample node towards the side of the obstacle that faces the exploring tree. Here we show an example. In this graph, D is the newly sampled node, and A, B, C are the nodes already in the exploring tree. B can be connected to D with a primitive of the lowest cost. If we are using collision inclusive planning, we would generate a collision node on the left of the obstacle. However, if we are using collision-exclusive planning, C will be connected to D, and the exploring tree would actually expand to the right of the obstacle at this specific step. With experiments, we find that the benefits of planning with collision often outweighs its cost when planning a narrow environment. Here is an illustrating example. We try to find a trajectory from N0 to Nf. The blue curve is the trajectory found by the planner, and the blurred circle is an intermediate node on the trajectory. The solid blue rectangles are the obstacles. The green triangle dots represent a sampled node that does not have collision in the exploring tree, whereas the red nodes are the collision nodes added to the exploring tree. We did a Monte Carlo test by run this planning experiment for 1 million times and plot out the mean trajectory time against the computation time. We find a collision-inclusive planner can find a faster trajectory here with less computation time. We also plot out the number of nodes in the exploring tree against the computation time. This partially provides an explanation of why the planner with collision works better in this narrow environment, because it can add nodes to the exploring tree faster, and this contributes to the better overall planning result. We carried out an experiment on tracking the planned trajectory with our collision-resilient aero vehicle. In this experiment, the vehicle is trying to move from the left half of the space to the right half while circumventing a table in the middle. Here is a video. First, we show the no collision case, and then we look at the case with collision. We see that the vehicle successfully tracks the collision-inclusive trajectory. Moreover, as it takes advantage of the collision to change its momentum, it avoids carrying out an aggressive maneuver, as it did in the collision-exclusive case. To conclude, we designed a sample-based collision-inclusive trajectory planner for multicopters, and the planner can improve the planning performance in narrow spaces like tunnels. We believe a potential extension of the algorithm includes intelligent selection of the planning with or without collisions, or use a mixture of the two to get the best of both worlds. Last, I would like to acknowledge Berkeley Fellowship for Graduate Studies to support this work. I would also like to thank the support of my lab mates from High Performance Robotics Lab. Thank you very much for your attention.